Okay, welcome everybody. So today we have Martin Schmaltz from BU, who will be telling us about cosmological anomalies and interacting dark sectors. Before we start, let me tell you that we're going to dinner and we're meeting at 6:30 here in the lobby. Everyone is coming. If you're planning to come, please tell me before 4:30 so that we can make a reservation. Thanks.
Thank you. So I see it starts when Nati walks in. The seminar. Good. So I would like to tell you what Juan told me I should, a good topic would be to give you a bit of an update about the cosmological anomalies that people are talking about, what happened recently, what are the anomalies, and I'm going to give you a biased view of that, of course. So I have biases a little bit, but I'll try to be fair. Most of the biases are in the selection of what anomalies I tell you about. But I'm getting a little bit ahead of myself. Here are my collaborators over the last few years. I'd like to highlight in particular Kara. Here's an NYU student who is currently graduating and is looking for a postdoc position. She worked with me on Big Bang Nucleosynthesis and is an expert on that and has the best code on Big Bang Nucleosynthesis that she largely wrote. And Hengami here is a Harvard student with Matt Reese. And we worked on large-scale structure models together, and she's also graduating this year. Both are excellent students. And Ishwar is not quite ready. All right. So an outline of my talk is, so I'm going to first tell you about the lambda CDM desert. This is something that we noticed. It's nothing deep, but it's kind of like the particle physics desert, grand unification desert, and I want to show it to you. And then talk about some of the tensions, the cosmological tensions that exist in the desert. Two of the most important tensions that people talk about all the time, and I will also talk about, are the Hubble tension and the large-scale structure tension. And the large-scale structure tension in particular, like the Hubble tension now, also has early and late solutions. And so I want to tell you one example of each of that and what it has to do with Lyman Alpha data. And then finally, at the very end, after I finished, perhaps in the questions, I'll tell you about what's going on with the lithium anomaly and summarize. So here's the lambda CDM desert. So it's a very simple plot. Here is the energy scale, and here are the particle masses in the standard model. And you have to, so this is really the bars here are the masses. And you see that there is a big gap here in the particle spectrum in the standard model. At an MeV scale, half an MeV is the electron mass. And all the QCD states are, of course, above there and the fundamental fermions. And then there's nothing for a very long time. And then down here, you get the different mass eigenstates of the neutrinos. There's a big gap here in the particle spectrum, the fundamental particle spectrum. And coincidentally, there's also a gap in the important scales that are important for cosmology. So here also at the MeV scale is our nuclear binding energies. That's a coincidence that the electron mass is around there. And also the weak interactions decouple at around those temperatures. So when the universe cools down to these temperatures, weak interactions decouple, nuclear binding energies are there, the electrons annihilate away. It's all happening at more or less the same scale. And then nothing happens for a very long time. The universe just expands. There are no particles annihilating. Just it's very boring and simple. And boring and simple, of course, means that we are able to calculate stuff. And so we can make predictions here relatively easily because there's no complicated physics in the standard model going on. And then down here, the EV scale is when recombination happens. That's where the CMB is released. And that's because the atomic scale is down there. Right? Atomic binding energies are down there. And so there's interesting stuff going on again. But in between, there is this desert where nothing happens. just the universe is expanding and cooling down for 6 orders of magnitude.
What was M2?
M2 is the second mass eigenstate of the neutrino. So so this was assuming the normal hierarchy. There's a heavy mass eigenstate, a lighter one, and then one that might be massless. But there is data in the EV to MeV desert, and that's what makes it interesting in cosmology. And so in particular, the CMB. So the CMB photons, as I told you, are being released when hydrogen becomes neutral. That is at about the temperatures of an EV. And so here's the CMB spectrum shown in terms of the usual multipoles, but it has to do with temperature because the different multipoles enter the horizon. So modes of those wavelengths enter the horizon at different times. The shortest wavelength modes enter the horizon at earliest times when this is still the hottest. That's at around 100 eV. And then the middle of the CMBs, the main peaks of the CMB are entering the horizon at around 10 eV to an eV. So momentum modes, Fourier modes in the primordial fluid that have these kinds of wavelengths corresponding to sizes of fluctuations on the sky, corresponding to these sizes, enter at different times and are therefore sensitive to physics that's happening at those times. So for example, if you had a particle with mass 10 eV and that was annihilating away, that would change the Hubble expansion rate at that time, and that would change the evolution of everything that depends on timing, which is what the Hubble expansion rate gives you. And so you would see that as some sort of dip in the CMB. Large-scale structure data is actually sensitive to a wider range, and it goes to even higher temperatures. So this is a similar story. So again, these are modes that are entering the horizon. So this, what am I plotting here? This is the matter power spectrum as a function of wave number in the universe, right? So you have some wavelength fluctuation. That wave number is k. So over here, we're looking at very small scales. Here, we're looking at large scales. And the density fluctuations in matter in the universe are roughly described by this black line here that comes from the Lambda CDM model. So there's a peak of the density fluctuations at modes that are entering at equality. So roughly temperatures of an EV. And these smaller scales, so over here we're at galaxy cluster scales. So over there it's galaxy scales. Those scales are corresponding to modes that are entering the horizon earlier and are therefore sensitive to what's going on at higher temperatures.
Could you remind me why this power spectrum is not scale invariant? The primordial is scale invariant.
So this part here is scale invariant, and this part is not. And this has to do with the growth of the structure. And the growth of structure happens mostly during matter domination. And so these modes are all entering. So naively, you would want to extrapolate it this way. But these modes here are were all inside the horizon throughout matter domination. And so they all grew a lot linearly. So they grew by about a factor of 1,000 in delta. And so 1,000 squared in this during matter domination. Modes over here were entering during matter domination. So they only grew for part of the time. And the mode that's all the way over here is entering today, so that hasn't grown at all. Okay, so the scale invariant spectrum is here, it's scale invariant because this is all outside the horizon. And here it's scale invariant again because roughly because they all grew the same because they all were inside the horizon during matter domination. And during radiation domination, there's not much growth.
Scale invariant, but scaled by 1,000 squared.
Yes, that's right. All right, so if there's something going on during matter domination or earlier during radiation domination, so these modes are already inside the horizon during radiation domination, There's a little bit of growth during radiation domination. It's slower than during matter domination, but if you're changing expansion rate at those times, for example, that would imprint on here as well.
So why there's only little data in the low energy regime?
Sorry, why is that?
Are those points in different data?
Yeah, so the points are all different kinds of data sets. This stuff here on the left is mostly CMB, and it's actually data, not directly data from this. It's not the matter power spectrum that's being measured here. This is actually the CMB. And then there's some assumption that how you translate fluctuations in the CMB into fluctuations in the matter. So don't worry too much about this. So when we're talking about large scale structure, we're talking mostly about this data over here. And that data comes from counting galaxy densities or galaxy cluster densities or weak lensing measurements. And then from the other end, from the upper end of the MEV desert, you have Big Bang Nucleosynthesis. That's the grand unification of this desert. And in Big Bang Nucleosynthesis, what's the action is between an MEV and 100 keV. This is so at an MEV, you still have protons and neutrons. And when you get to this temperature here, temperature is dropping as we're going this way. The abundance of deuterium, which is this red line here, all of a sudden goes up. This is called the deuterium bottleneck. So suddenly you start making deuterium out of protons and neutrons. And then very quickly that deuterium gets processed into hydrogen. So Y here into helium. So Y is the helium abundance. And everybody else's abundance drops a lot. And then afterwards you have only, to first approximation, you have only helium going on here, only helium and hydrogen, that is protons, but there are small residual abundances of deuterium, helium-3, lithium somewhere down here, lithium-6 even further down there. And all of these abundances here depend in detail on nuclear physics cross-sections, which we can measure in the laboratory, and then on the expansion rate of the universe back then, on how many baryons you had in the universe, the abundance of baryons. And so there are a few cosmological things that you can learn by predicting these abundances and trying to compare them to data today. And you see the scales where things are set are, MEV to 10 keV. So if you have new physics at those scales, that would impact BBN. So here's a little summary of the desert. So from EV to MEV, as I was just telling you, BBN measurements are sensitive to these scales here. The CMB is sensitive to those scales, and large scale structure is, I think this one is a little too optimistic here, how far I drew that. And there are a lot of measurements on these things today, and the future brings a lot more experiments. So
What is BBN future? Of what?
in BBN, well, so right now what we're measuring very precisely is helium and hydrogen. I think that's probably mostly what it's going to be, and we're going to get more precise. In deuterium and helium is what I wanted. So always the ratio to hydrogen. And in deuterium, there's actually a little problem which I wanted to tell you about that with nuclear cross sections that we still need. And so depending on which camp you believe, you either predict the right amount of deuterium or you don't. All right, but also in the desert, because there's data there, and there's some part of the data has multiple different techniques, and there are some tensions there. And so these I want to tell you about. And the most famous of them is the Hubble tension. So I'm going to spend a little bit of time on the Hubble tension. And then large scale structure, that's also known as the S8 tension. And more recently, people are talking about F sigma 8. Maybe that might be a tension. So I'll tell you what those things are. And then let's begin. But let me start with the Hubble tension. So the Hubble tension is probably almost certainly the most significant of them. It's about 5 sigma. And I would like to briefly remind you what the Hubble tension is. So there's 2 classes of measurements of the expansion rate of the universe, so Hubble. And let me start on the right-hand part. So what are these plots that you can't read? So all of these here are different kinds of measurements. And what they find for the H naught parameter, down here is the axis of H naught, the expansion rate. And so in the usual units, it's either 67, that's this purple line, which is found by that experiment. This is the CMB here. Or it's it's this, which is measured by supernovae. This particular data point here is the supernovae measurements. And so why am I saying there are 2, and obviously they disagree, and this disagreement is the 5 sigma that I just told you about. So what are the 2 classes? These here over here are all measurements of the expansion rate using the Hubble law. And the Hubble law is very simple. It's just you look at a very far away object. You see how quickly it's receding because of the expansion of space in between. You measure that recession velocity using the redshift. So that's very easy. If you actually see something, you can always see the redshift from some spectral line. And then you divide that by the distance. So it's the velocity by the distance, that's Hubble, the expansion rate. And the distance is the hard part. So knowing how far away something is, usually what we do is we assume we know what Hubble is from some other experiment, and we use that to determine the distance. But actually getting the distance is hard. But there are many different techniques, as you can see here. So the different colors correspond to different techniques. And I want to tell you what's new in some of those techniques. And so there's some news from this summer. And what about these? So these measurements are measurements of the CMB, or baryon acoustic oscillations. And they have in common, all of these measurements, that they use one particular quantity, the sound horizon, which I'll also tell you what it is, as a standard ruler. And so in order to do the measurement, you need to know what the sound horizon is. And that sound horizon is something that we calculate in the lambda CDM model. The lambda CDM model has parameters in it, so you have to fit those parameters to the CMB and PAO. Once you have those parameters, you can calculate what the sound horizon is, and then you can do this measurement. So it's interesting that all of these use the sound horizon, whereas all of those don't. And so if we got the sound horizon wrong somehow, then that could be a possible resolution of the Hubble tension. So a lot of theory effort has gone into building models that change the sound horizon somehow to try to change the prediction of this thing, which then means for a different Hubble. All right.
So the sound horizon is just a property of the plasma, right? It's just
the sound horizon is
determinable but from first principles.
From first principles, except if you don't know what the ingredients of the plasma are, for example, or if there's a different expansion rate at that time.
In lambda CDM, is treated as a free parameter, or it's attempted to be calculated?
So in lambda CDM, you assume what all of these things are, and then you calculate.
Oh, good.
Yes, that's right. All right, but first, before I get to this, I want to talk a bit about this, because this is where the news is. There wasn't much news here recently. So first of all, these measurements up here are all supernova measurements of the expansion rate. So the distance to faraway objects that we're seeing receding is being determined by supernovae, and I want to tell you the update on that. These measurements here use galaxy sizes. Right, the difficulty is always knowing how far away an object is. If you knew what the sizes of galaxies are, then you can just look at those galaxies and you can measure the angle. That is easy to measure. And you see, if you knew what the galaxy size is, that tells you also what this distance is. And so those are determined through some relation, astrophysical relation, that's called the fundamental plane. Here are strong lensing measurements. So these are the Einstein rings and multiple images, strong lensing technique. Here's a technique using galaxy ages that uses a lot of astrophysics, so I don't particularly A, understand, B, trust this. And then this green stuff here, so these two I'm not going to tell you anything about. This is gravity waves, so this is LIGO, neutron star mergers. If you have a neutron star merger, you can see something, so therefore you can get a redshift. And then from the shape of the gravity wave, you can extract the information that you need to get the distance. Unfortunately, there's only been one of these events, and it's now many years ago that we had this one event. And so different ways of analyzing this one event can give you different central values and all with big error bars because there's only one event. Okay, so let me start with the supernovae. So the supernovae, so the idea there is supernovae are very uniform in their brightness, and I'm simplifying here. And so the further away a supernova has been, the less bright it appears. So you measure the brightness, it tells you how far away it is. But we don't know the intrinsic brightness of supernovae, so we need to calibrate. And we calibrate by constructing what's called a distance ladder. And this is exactly what it looks like. So here is Adam Rees and company, the SHOES team's distance ladder schematically. And what's shown here are, so these over here, these are the supernovae. Each of these dots here is a supernova. And this is a distance versus magnitude diagram. I don't want to go into the details of explaining this, but the point is, these are the large distances. Over here are the small distances, and supernovae is what we're measuring. And the red ones in particular are the ones that are being used for the extraction of Hubble. But as I told you, we need to calibrate the brightness of the supernovae in order to be able to use them to determine the distance. And that calibration is being done in this box here. So these are intermediate distances and we're now so close that to us that the volume is relatively small and that there have only been 42 supernovae that went off in the last 40 years or something like that, that we've been actually looking at these things and taking spectra. So this box here contains all the 42 supernovae of the past 40 years. And these supernovae are all in some galaxy. And so we need to know what the distance to that galaxy is so that we know what the distance to the supernovae is so that we can calibrate supernova brightnesses. And to determine the distance to the galaxies, we use stars. We use particularly bright stars called Cepheid variable stars that are also very uniform in brightness. But they're not as bright as a supernova. So the furthest you can see the Cepheid variable stars is to within here. You can't see them over there. So you use those Cepheid variable stars to calibrate the supernovae. And the Cepheid variable stars themselves need to be calibrated as well. So you also need to look here, Cepheid variable stars in the Milky Way, the Large Magellanic Cloud, the Small Magellanic Cloud, that's the newest contribution from this year, and some other nearby galaxies.
Dumb question. The geometry, the bottom rung of the ladder is just parallax?
Bottom rung is parallax, and there's a little bit of other stuff as well. But
So
it's
there's
mostly
parallax, which is honest truth, and then
Yeah.
there's a straight line fit that seems to work. Is that?
so you determine the brightness of Cepheids, and they have the period, luminosity of relation, all of that. So you determine their intrinsic brightness by using parallax. In the Milky Way, in the Large and Small Magellanic Cloud, and in these galaxies there.
But it's supposed to be non-trivial? These are on a straight line?
That is supposed to be non-trivial, yes. Yeah, so here that there is some spread here, for example, some of these supernovae here.
So I mean, all the sort of very dumb, super old questions, like how do we know the supernova, long ago supernova aren't a little different than now, all that stuff about,
That's all in.
all of that's in here, and
Yeah.
and the response to why we shouldn't be worried is that the fit is very good.
And I mean, the supernovae, so the biggest problem with this whole thing is, or the biggest experimental error right now is with the supernovae, because the supernovae actually aren't all the same brightness. They need to be, so some of it has to do with parameters that you can fit for, and some of it just seems to be random. And so you need to average, so there's a 5 to 10% random fluctuation in the supernova brightness. And so you need to average over 42 of them to get best possible result. And if we had, 200 of them there, that would. So that's the biggest chunk of the error budget here is so that there are only 42. And anyone who uses less supernovae here, say they only use 10, have automatically a factor of 2 bigger error bar there. All right, so what's the news? The news is that there's also Friedman versus Rees tension from this August. So Wendy Friedman from the Chicago Supernova Hubble program released a paper where she showed new calibrations or different calibrations of the supernova brightness. So here, this is part of the Hertzsprung-Russell diagram. This is the giants region, the brightest stars. And in these brightest stars, here are the Cepheids, the black dots. They're very special stars, but then here are some stars that are called the red giants. And this line here is the tip of the red giant branch. And we believe we understand or can parameterize at least the astrophysics of that, where that tip is. And so if you look in different galaxies, look for the tip of the red giant branch, that should always be at the same brightness. And here are some new things that are called J regions, something. And so there's a blob of stars here, and that's also always in the same place. And so she used these to calibrate supernovae, those to calibrate supernovae, and those to calibrate those. And then 9 days later, that's always what happens with Adam Rees. If you criticize his work, 9 days later, there'll be a paper telling you why you're wrong. And it's quite convincing. And so he did the same thing, also calibrated supernovae with the 3 different stars. And the bottom line is this. So these are 3 different kinds of stars that you can use to calibrate supernova distances. And forget about the supernovae for a moment. It's 3 different kinds of stars that you can calibrate distances to anywhere where there are those 3 different kinds of stars. So some galaxy that has all 3 stars, you can look at all 3 stars and see whether you get the same distance. And what Rees shows quite convincingly is that you do get the same distance. So this axis here is a measure of the distance that you extract. These are the different stars. There are only 3, but so tip of the red giant branch, that's one kind of star. This is the other kind, and Cepheids and Mira stars is another one I didn't talk about. And so Cepheid calibrations from Shoes, which is Rees, and Wendy Friedman agree perfectly. Tip of the red giant branch is pretty close. And these JAG B, JA, GB are also pretty close. Just for scale here, you would have to be off this much in your calibration of the distances in order to resolve the Hubble tension. So I think this is very good confirmation that these different kinds of stars all give you more or less the same distances. So it's not one of the things that people have always criticized. Well, we don't understand the Cepheid variable stars that well. They're kind of complicated. And maybe the calibration of supernovae is just off. So now I think we're much more confident that that calibration may be a little bit off, but not that much off. Certainly not enough to account for Hubble tension.
So some time ago, I think people said that this tip of the red giant was in between the 2 measurements. It's changed now.
Yeah, so that was Wendy Friedman, and you are asking the perfect question for the next slide. Unfortunately, this one is maybe also not very legible, but so this is also from Adam Rees's paper. And the differences in the H0 values that Wendy Friedman gets and the Shoes team get has to do with the supernovae that are being used for calibration. So Wendy Friedman does not use all the 42. I think because she doesn't have access to the precise data of all the 42. And so she uses a subset. Here are the galaxies of the 42 supernovae, and they each have a little number associated with them. And they tell you if you had left out the supernova here, that would give you, sorry, if you just use this supernova for calibration, it would give you an H naught that is smaller by 0.7. If you just use that one here, so there's some that are plus 10, and so those are the largest fluctuations. And so she uses a subsample of these. And within that subsample, if you just use Ries's measurements, but only apply to that subsample, you get an H naught that's different by about 2.5. And that is the distance between Ries's measurement and the halfway in between that you're remembering. So that's that. It's as simple as that. In fact, so this the new Wendy Friedman paper was about using James Webb in order to observe the stars, and it's better for the tip of the red giant branch stars and those JAG-B things. And so these James Webb calibrations turn out to be the same to within errors as the Hubble Space Telescope ones, which Ries has been doing. But so the new results are all about James Webb, but they haven't had enough time yet on James Webb to observe all of the supernova hosting galaxies. And so both groups have gotten time for 11 galaxies, and they chose 11 different ones in here. And Ries chose ones that are higher in the value of H naught, and Wendy Friedman chose ones that are lower, not on purpose, but they're, Wendy Friedman was after being able to observe something particularly well, and I don't know what. They want to use all of them, but it takes time. So they haven't had enough time yet to do all of them. But Shoes has done all of them with the Hubble Space Telescope. That's been around for a long time. They've had enough time. And so if you use all of them, you get Adam Ries's value of 73.
Then there's no tension between these two groups after all.
So the bottom line is there is personal tension between those two groups, but I think there is very good agreements between the three different ways of calibrating distances. But that doesn't matter which supernova or galaxy you're looking at. You're just looking with three different stars to the same galaxy, and you have to ask, do I agree on the distance? And they all agree on the distances quite well. So it's not the calibration of the supernovae. And then if you use all of the supernovae, you get this.
But the differences between different subgroups of supernova, are they statistical or systematic? Or should one worry that if one takes half of them and gets?
I mean, you know the real answer because you have looked at all of the supernovae with the Hubble Space Telescope. So you can compare to that. And I think it's like 1.5 sigma is the biggest difference that you get. I mean, Wendy Friedman's 11 supernovae, I think 8 were below the average in brightness and 3 were above. And so that's where the difference comes. And what you should be doing is you should have a complete set somehow so that you don't have selection bias. The 42 is a complete set because it's all the ones that we could see. You can also just draw a line and say, I'm only going out to a certain distance and take all of them up to there. You can do that with the Wendy Friedman and Ries ones because they happen with JWST, because they happen to have observed more or less orthogonal ones. And so if you combine theirs, you again get that 73, but with a larger error bar because you don't have 42 calibrators, you only have 25 calibrators.
I guess I was trying to ask, in this complete set, does it look like sample from kind of reasonable distribution or
Yes.
like this?
Yes. Yeah, there is no sign that there's anything weird going on.
What are these 42 all the galaxies with supernovas that are close enough to observe these stars?
That's right. So there's 39 galaxies and 42 supernovae because 3 of them had to.
Yeah, with supernovas and Cepheids, right? That's
It's supernovae that are close enough that we could have seen the Cepheids also in that galaxy at enough precision that you can actually do a measurement. That's right.
Sorry, Martin, why isn't there like one of a square root 42 level error in everything? Like, where's that T small error coming from? Why isn't that just the small number?
Oh, because they are actually more or less uniform. The supernovae, they don't fluctuate by 100%, they fluctuate by, 8% or something like that. So you need to divide that by square.
By another.
Okay. All right, so this is that's what's new with the supernovae with the Wendy Friedman versus Chicago group versus the Shoes team. I think the Shoes team is always defending their measurement quite well. They're the only ones who have done all 42 with the same instruments so that different ways of calibrating cancel out. And so I believe this number here. Okay, so that was these measurements up here. There's a whole host of other ways of determining the distance to some object that's receding from us, and therefore we can measure Hubble. So there's galaxy sizes in the fundamental plane. This is all very small print, but so there's an astrophysical way of determining the distance, which is you have some galaxy with stars going around. Because the stars are going around, there is some redshifting and blue shifting as stars are coming towards you and going away from you, redshifting and blue shifting of spectral lines that broadens the spectral lines. That broadening of spectral lines tells you about the velocity of the stars. So that velocity dispersion and the overall brightness of the galaxy has some relationship that's called the fundamental plane to the size of the galaxy. So if you can measure the velocity dispersion and you can measure the overall brightness, there's some phenomenological relationship that tells you what is the size of the galaxy. And then you can look at the angular size that you see and you can infer the distance.
By phenomenological, do you mean that they just like plotted it and then did a fit function? There's no deep reason for it?
I mean, there is some reason, which is, so there are models that roughly get that thing right, but like that it's serialized and right. If you make simple enough assumptions, then you can actually calculate and so you have models. But yeah, you can also just plot and you see that there's the plane. And so DESI did this and they released a result that they get a Hubble of 76 plus minus 1.3. But this fundamental plane also needs to be calibrated. So there's some overall offset in where the plane is, and that needs to be calibrated. And they use the coma cluster. So they looked at a bunch of galaxies inside the coma cluster to do the calibration, but they didn't have a very precise distance to the coma cluster itself. That was the biggest error bar. And so it's a plus minus 6%. And then Adam Rees said, well, there are supernovae in the coma cluster. I can calibrate the coma cluster for you. And so this is not a totally independent thing, but if you calibrate the distance to the coma cluster, you get 76 plus minus 2 for Hubble. So in perfect agreement with Rees, not in agreement with what you get from the CMB. And on this plot here, what I'm showing is what are coma cluster distances. So these are coma cluster distances here. This is Adam Rees's new measurement of the coma cluster distance. This is what the distance to the coma cluster would have had to have been for consistency with the CMB measurements. And all of these here are older measurements of the distance to the coma cluster using a host of different techniques. The coma cluster has been one of the playgrounds of astrophysicists, and so the distance to it has been measured many times before. And you see none of these measurements have the coma cluster as far away as it would have to be for there to be no Hubble tension between this direct measurement and the CMB. So even if you don't believe the supernova, if you don't believe this point, all of these points, none of them have a coma cluster as far away. It would have to be for there to be no Hubble tension. What about strong lensing? That's also a fun one. It's fun to think about, and there's some interesting news. So note, there is a little bit of a scatter here. So most of the strong lensing results are where all the direct measurements are, and then there's one of them that's all the way over here, where the CMB value of H naught is. And so what's strong lensing, or strong lensing with a time delay? So here's a typical image like that. You have a foreground galaxy. Here's the foreground galaxy. That's called the lens. And then in the background, so you are here, the galaxy is, the foreground galaxy is there. And then in the background, you have an active galactic nucleus, an AGN. And that AGN image that you see is strongly lensed, and you actually see the AGN 4 times in this particular image. In perfectly symmetric situations, you would see the famous Einstein ring. These are not quite on an Einstein ring because that lens is an oval thing. It's an elliptical galaxy and not a perfect sphere. And this image here, seeing all of that, is enough information that with some simple assumptions, you can reconstruct what the mass profile of this lens here is. So you have to assume something about the mass profile. You have to make simplifying assumptions, and then you take this image and then you reconstruct carefully what the lens is that gives you exactly this image. And then when the thing that's being imaged is actually an AGN, AGNs are time dependent. Their luminosity is time dependent. And that's interesting because these different images here arrive at different times. And so you see, and the interesting thing is that takes on the order of a year or so. The time delays are of order months or a year. And so you see some characteristic feature in the AGN. Maybe it becomes particularly bright at some point of the year. And that characteristic feature is here at some point, and there it's half a year later, and there it's maybe 3 months earlier. And so by time shifting those things, you can measure what is the time delay in the images. And that time delay, if you can measure, so you measure the positions of these, you reconstruct the lens, and then you measure the time delay. That time delay allows you then reconstruct the distance to the lens and the distance to also the AGN. So if you have all the information, you can get the distance. Again, redshift is trivial because you see stuff, and then you can measure Hubble that way. All right. So here is a little bit of history of their results. So this used to be called, the collaboration used to be called Holy Cow. They got 73 plus minus 2, more or less. Then they got absorbed into a new collaboration called TD Time Delay Cosmo. And they got more or less the same answer. And then people have been yelling at these people for a long time, saying that the mass profiles that they assume for the lens are too simplistic. And if you allowed more general mass profiles for the lens, then there would actually be an other parameter. And that parameter is basically what is the gravitational potential at the radius. So if you go into the plane of the lens, what is the gravitational potential where the light from this guy here actually passes through? So that gravitational potential is responsible for the time delay. And different lenses, and so there's at least a 1 parameter family of different lenses that give you exactly the same image, but have different gravitational potentials there, and therefore give you different time delays. And this is called the mass sheet degeneracy. So there's a mathematical proof that you can actually do this, that there is a 1 parameter family. This is for potentials that are mathematical and not very interesting in practice. But even for potentials that are interesting in practice, and I should show you that here. even for potentials that are interesting in practice. So here's a density, 3D density profile. So this is the center of the lens galaxy. This is the outskirts of the lens galaxy. Here, these lines are the dark matter density, and this is the baryonic density. And there are small shifts here proportional to a parameter, and you get a total density profile, which is what does the lensing. And so this total density profile is a little bit different around here. And that little bit of a difference in the profile gives you a little bit of a difference in the gravitational potential. Or what's inside gives you a little difference in the gravitational potential, and that little difference gives you a different time delay. So it's the exact same image that you see, but different time delays. And therefore, you reconstruct a different difference, therefore distance, therefore you reconstruct a different H0. So they parameterize this with this parameter lambda sub c. Lambda sub c is how much non-standard profile are you assuming, or non-simplistic profile are you assuming? Lambda equals 1 is the old profile that they used before. Lambda bigger or smaller than 1 is deviating from that. And here you see from their old paper how H0 depends on what you assume this lambda is. And you see it is basically linearly proportional to lambda. So if you don't know what lambda is, you don't have a measurement of H0. And going back to that table here, that's what happened in going from here to there. Here they didn't assume anymore that they knew what lambda is, and all of a sudden the error bars exploded. They didn't become infinitely large because you can actually determine a little bit about what the mass profile is from stellar dynamics. So you try to, it's the same thing that I just talked about before. The widening of lines, of spectral lines, tells you something about the velocities of stars, and that tells you a bit. And so that goes in here. Now then these people had a clever idea. This was still in that same paper. This is a paper from 2020 where the error bars exploded. They said these lenses here are presumably ordinary elliptical galaxy. The only thing that's special about them is that they happen to have an AGN behind them that is being lensed. But if we look at an elliptical galaxy that looks the same, but has an ordinary galaxy behind it, and we also reconstruct something like this, we can study everything except for the time delay. Ordinary galaxies are not variable in brightness, only AGNs are. We can do the reconstruction so we can do the same, we can run the same reconstruction, and we can also look at the velocity dispersion of the stars in those other lenses, and we can try to learn, is there this mass sheet degeneracy in reality, or is there not? In other words, what is this parameter lambda? And the advantage of looking at other galaxies is that you can also look at closer ones where it's easier to see the stars going around, and so you can actually do this measurement more easily. And so that's what they did, and they found that lambda is actually 0.91 or something like that. And so there is a mass sheet degeneracy, and that shifted the value of their H0 that they extracted from the Reese value to the CMB value. Yeah.
Was the unexpected mass sheet interesting physically? Where it comes from, or is that not interesting?
It's, whether you have more mass in the baryons or more mass in the, so one of the ways of getting a mass sheet is put more mass in the baryons, less mass into the dark matter.
Okay.
Another way of doing it is to have the dark matter profile change by having the dark matter have a core or not have a core. So it's pretty easy to imagine that that's possible. Now, this is not the end of the story, however. So now we're coming to the news of the summer. This summer, the same group, actually these are the same or a subset of the same authors of TD Cosmo, looked more closely at the same story again, galaxies that are being lensed by galaxies, and to go more precisely after the mass sheet degeneracy. The first time they did a somewhat half-assed job, it turns out, and now this summer they released a paper they looked very carefully. Again, they did new precision. I mean, they got telescope time to look at those galaxies more precisely, have better imaging, and they find lambda as 1 for all. Now, they didn't release a new value of H naught because they were not the whole collaboration. And so all they did is remeasure H naught, measure the mass sheet degeneracy parameter. But you and I can now look at their plot and we can say, well, if you go to lambda of 1.02, you read off the value of H naught at 74.5. What you can't do quite as well is guess how much systematic error they're going to associate it with this situation that we're in now. So naively, you would go back to the old error bars because this plus minus 0.01 is smaller than all the other error bars. And so you would just say that whole mass sheet degeneracy story is over and we're getting the old values. They're also looking at new strongly lensed systems now. And so the next update of H naught will have new strongly lensed systems in it as well. But I think this, it used to be for 4 years. If you were asking people what does strong lensing give? Does it give 74, 73, or does it give 67? It really depended. It's either one of those. That seems to be over. They're all now back to getting the high value, confirming the Hubble tension. All right, so let me summarize the Hubble tension a little bit. So it certainly does not look like it's going away. If anything, it's getting stronger, which is what a real problem should do. As the data gets better, the tension should be stronger. So it's now 5.7 sigma with the latest value of H naught from Shoes from Adam Gris's group. The CMB gets 67.5 plus minus 0.5. This is, all of these are statistical and systematic as far as we understand the systematic errors. And this is the 3 Planck, ACT, and SPT all combined, the 3 CMB measurements.
How much?
BAO gets something similar, but slightly.
How much of that is Planck? Is that?
Planck has the smallest error bars. So I think if you did this with just ACT, you would get plus minus 1, maybe something like that.
So it's not like you could remove the tension by removing one of the instruments.
No,
That's what I see.
yeah, you can't.
And if you just do BO, if you just completely discard CMB, then.
If you discard CMB, that's actually this. That's just BAO. So still there. So all of these, as I was telling you, use the sound horizon RS. And what is the sound horizon? So it's the distance that perturbations in the baryon photon fluid travel from the beginning of time until the baryons and photons decouple, which is when hydrogen becomes neutral, when the CMB is being released. So that distance, so you start out with some perturbation in the baryon photon fluid, it travels with the speed of the baryon photon fluid, so the sound speed in that fluid, and that's a distance here, and it's a integral over time because things are varying in time of the speed of sound times time. And if you rewrite that into more convenient coordinates, instead of time, use the redshift. It's an integral from the redshift of the CMB to infinity and over the sound speed, dz divided by square root of Hubble. And Hubble is given by at those times, and that's given by the energy densities in all the fluids in the universe at those times. So if you could change the sound horizon, then you could change all of these measurements at once. And so the idea, of course, is you try to change the sound horizon to there. That's about a 7 or 8% reduction in the sound horizon that you need to achieve. So you need to change physics by almost 10% at those early times. Either you want to change the sound speed of the baryon photon fluid, but that's very simple physics, and you would actually have to change the baryon photon fluid. But the baryon photon fluid is what you impact that is what you actually measure in the CMB. At the end of the day, you measure those CMB photons. So if you muck around too much with the baryon photon fluid, the CMB will affect. So this is not an avenue that people take, changing CS. You could change Z of the CMB, recombination, the redshift of recombination. Those are the crazy models where people say, well, maybe the electron mass was different at recombination from what it is today. How would the electron mass be different? Well, you could couple the electron to some scalar field, and that scalar field is evolving. And so models like that, there are constraints on them, and you can't couple the field linearly. You have to couple it quadratically. Otherwise, the changes in the electron mass today are too bad for atomic clocks. But if you change it, if you couple it quadratically, it's still okay. So that works. You have to make a couple of other changes at the same time to not screw up the CMB, but that actually sort of works. That doesn't get you all the way. None of the Hubble tension solutions get you all the way. So that's one of the puzzling things. So all this RS stuff here, they're always bounds on how much you can change RS. And typically you can raise the 67 here to the maximum of 71, and that's where it really dies. Now 71 is not that different from 73 plus minus 1. So maybe that's the solution of the Hubble tension, a little bit of a 1 sigma fluctuation over here and a 71 here. But changing the electron mass is already somewhat out there. The easiest way of doing it, but doesn't work quite as well as changing electron mass, is to postulate that there was some other energy density at early times. And that is what early dark energies, for example, is about. So you just assume that there was an extra energy density here that makes this thing bigger. It's only there at early times and not there anymore today. And that would change the sound horizon. Now that also changes other things in the CMB. That depends on the Hubble expansion rate. And so that's why it's a non-trivial game.
Is it still true that if you make a 10% change back then, it still has to, after recombination, die a lot more quickly than radiation?
So if you do it with radiation, which is what I've done a lot, you get to, depends on the exact details of your radiation model, but you can get to 70, 70.
Oh, I see. So that whole thing was assuming that you're trying to get the whole thing.
Yeah, so if you're trying to get the whole thing, nobody knows how to do that. Getting to 70, 71.
With linear radiation, I mean, you could imagine some I don't know, something that turns into a kinetic energy rolling scalar or something like that. It goes like 1/86.
Yeah.
So if you have something that's like 10% back then, but then just decays a lot faster than radiation afterwards, does that get the whole thing?
It doesn't get the whole thing because, so what you're doing is you're changing Hubble, right? And so there are other scales that are imprinted in the CMB that are not measured as well as that the angular size of the first peak. And your messing built up as well. So your new energy density that you're adding needs to be added in just the right way so that the other scales are being changed in ratios.
Sorry. So there isn't like a simple story, like for about a factor of 10 in Hubble, like where you see the peaks, you add something, I don't know, you change Hubble by 5% around then, and then it just disappears after that, just way faster than radiation. That doesn't work.
So the sound, it doesn't work because the sound horizon is, I mean, it sort of works, but the sound horizon is this integral here over Hubble. There is the damping scale, which is another scale in the CMB, which in principle, nobody talks about it this way, but you could use that to measure Hubble as well. And you would be you're changing that damping scale at the same time but it doesn't scale in exactly the same way. So it's Hubble that's being measured is not being shifted in the same way as this Hubble. So the last thing that I want to say, and actually it's the last thing I'm going to say at my seminar, I think the time's up, is this thing that we just talked about is trying to change the sound horizon is incredibly hard, even though we're only trying to solve a 5 sigma problem. You're trying to solve it from the wrong end in a way, because you're trying to take this measurement here, which has an error bar of 0.5, and measured in terms of this error bar, the Hubble tension is actually 11 sigma. It's easy for a model builder to change a 5 sigma thing. But an 11 sigma thing is too hard. Right, so trying to change this prediction is incredibly hard because the CMB is so precise. And there are other things in the CMB that you keep screwing up when you try to change the sound horizon. And it's 11 sigma. So if there was something over here equivalent, then you would only have to fight that 0.9. And so it's a factor of 2 easier. But over here, these measurements are very direct in terms of what model building concerns. It's, you know, you look at an object, how far away it is and how far it's receding, that's directly measuring H naught. There's no room for model building there. And so there is a little bit of room for model building, but I think this is mostly crazy stuff. So, you know, these measurements depend on astrophysics. Of course, you could say that we don't understand any of the astrophysics, right? But it's getting more and more solid. Now 3 different stars for calibrating the supernovae. This measurement is a local measurement of the expansion rate. It's the expansion rate near us. Maybe we're special. But this is actually continuously connected. So it's Z's of less than 0.1 is what Shoes uses, but there are supernovae that go further and further out to Z's of 1.5. And there's no sign that there's somehow a phase transition somehow as you get to Z of 0.2, all of a sudden the expansion rate becomes different. There's no sign in that. So there's dense data. In fact, supernova measurements overlap with BAO measurements, and the BAO measurements get the CMB value of H naught. Supernova measurements, you know, get the supernova value, and so there's no room to play around with somehow saying that, oh, H naught is different where we are from the rest of the universe.
I have a dumb question. Is it possible there's some kind of selection bias that you're, I don't know, there's some distribution of the brightness of the things that you're looking for, and we're only seeing the brighter ones, something like that, just.
Sure, that sort of thing obviously could be there, and
Does it go in the right direction? I mean, something like that?
the supernovae that we see are, I mean, the problem is, I mean, the way the Reese measurement is done is you make a cut in redshift. And the supernovae out to 0.1, what is it? 0.1, they're all easy to see. And so it's not like, so, yeah, if you were to go all the way to the edge, then yes. But these people, of course, know that. And so they're, all of these things have estimates of the systematic error of selection bias in them. And, you know, Reese has been doing this for 10 years. He's been getting more or less this number for 10 years. That number has been shrinking. And people keep yelling at him for, you know, that, or for the Cepheids are no good. And so he keeps going back, measuring that more precisely, said, yep, you're right, there was a problem here. I shift the central value by a little bit and shrink my error bars by a lot because I have put in a systematic error for this, and now I understand it much better. So I think this is all I
Really stupid question. If we didn't add the arrows, if we added the arrows linearly and not in quadrature, what would they be?
So now you're really punishing somebody who does a very careful job.
I know. I'm just curious.
So in Reese's paper, there are 50 different systematic errors roughly. I think if you added, all of those linearly.
That's really unfair, I know. Sorry.
So you're encouraging him to.
I know, I'm encouraging, I'm just curious.
Yeah. No, I bet you could solve the tension. Yeah, no, but it's something he worries about. So he has a paragraph in his paper saying
I don't know why I honestly don't know why we have these things in quadrature. I really don't know. I mean, it's some assumption. I mean, it's a totally reasonable assumption, but it's.
Well, it's, so he's doing the statistics of the errors, right? So he's saying that, well, it's very unlikely that all my 50 errors are going in.
I understand. But it doesn't mean anything.
All right, so my time is up. It's a good place to stop because I would be starting a new chapter.
Tell us something about this.
Yeah. Tell you a little bit about that. All right, so the S8 tension has exactly the same kind of plot as the Hubble tension. It's only 2 or 3 sigma, and that depends now a lot on who you talk to. So this is a lot less solid because you have to pick your data. But there's a similar thing. There is a Planck measurement of S8. What is S8, you ask? So here is again a plot of the matter power spectrum as a function of K. This is the amplitude of the power spectrum. So the fluctuations in matter, the 2-point function. And at 8 megaparsecs inverse in K, or 8 megaparsec size scales, so this is galaxy cluster size scales, we can measure what the amplitude of the matter power spectrum is, and that thing we call sigma 8. And S8 is some slightly rescaled version of that. So S8 and sigma 8 are more or less the same. S8 is it's this, which is what most of the experiments are actually sensitive to. And sigma 8 is defined in K space like this with a window function. So this is the window function. So if you had measured something over here, you could extrapolate what your power spectrum looks like if you knew something about the slope. You had some model for what the power spectrum should be. You measured its amplitude here, then you can integrate it against that sigma 8 window function, and you get your value of sigma 8. And CMB measurements are mostly over here on to the left. So at larger scales, smaller K, and direct measurements of the matter power spectrum through various techniques that are all being shown here. So again, there are many different techniques. They tend to lie to the right. And so one obvious interpretation of what this problem might be is that the matter power spectrum is actually a little steeper. So what is the tension? So this value S8 from the CMB is 0.83, and 0.77 is the value that you get from, for example, weak lensing measurements, but also from the clustering of galaxies. You use galaxies as point particles tracing the matter distribution. And so if you have more clustering of galaxies, you get a higher value of sigma 8, for example. And so one possible interpretation is that the matter power spectrum has a steeper slope at large K, and then that would explain the discrepancy. See if I can make this a little slower, a little faster in a good way. So another possible interpretation, however, is time dependence. So when you're measuring the matter power spectrum with galaxy clustering, for example, you're looking at objects that are relatively close by at z equals a half or so, or up to z equals 1. So what's shown on this plot here is the same scale that I showed you before. This is K, so wave number. Here I'm looking at small objects. Here I'm looking at large objects. CMB is large. Matter power spectrum from galaxies is small. And here I'm looking back in time. So this is z equals 6 down to z equals 0. And when you're looking, for example, at the lensing of the CMB is sensitive to matter distributions going all the way back to the CMB. Now, matter didn't cluster until more recently, but if there was a big potential well at z equals 4, for example, that would do lensing. And so CMB lensing is sensitive to z's between 1 and 5. That's where the lensing kernel is the strongest. So the CMB is sensitive to lensing at earlier times, whereas if we're looking at distributions of galaxies at z equals a half, we're obviously looking at the matter distributions at later times. So there's two possible interpretations of the S8 tension, if it's real. One of them is that matter clustering is going more slowly at late times than we predict in lambda CDM. So something is stopping the clustering from matter at late times by a little bit, right? This is a small effect. Or it's at small scales that the power spectrum is suppressed relative to what we predict from extrapolating from large scales from the CM. So there are two classes of solutions. Note on this plot here, so here is where Lyman alpha data lies. So Lyman alpha lies at very small scales and at early times. So Lyman alpha gets two different answers in that if you had a solution that suppresses the matter power spectrum at large K, it would also be suppressing it at Lyman alpha. If you had one that only suppresses the growth of structure at late times, that would be suppressing it late times. And so Lyman alpha would show an unsuppressed matter power spectrum. So if you had good data from Lyman alpha that lies here, you could answer this question, which kind of solution is preferred? And so it's easy to build models that do either this or do that. Let me skip that part. And let me show you what Lyman alpha says. So here is a summary of what Lyman alpha says. Actually, I'll show you this first. So here's our matter power spectrum again. Lyman alpha data lies at relatively large K, and Lyman alpha can be simplified into telling you what is the amplitude and the slope of the matter power spectrum here. And so that's what's being plotted here. This is the amplitude in some units, and that's the slope. This is the power, so it's some power law in K, and this is the exponent of that power. And here is what lambda CDM predicts. And if you did a model, my favorite model with dark matter and dark radiation friction, so the clumping of dark matter is being slowed down because there's some friction with dark radiation, you get a smaller amplitude and a steeper slope at large K. So this is what you can predict with some new model. So here's what the data says, unfortunately. So this is the data that we fit to. This is some EBOS data from 2019, Lyman alpha data. This is a competing set, data set from XQ100 in 2017. They don't agree with each other. All of them want a somewhat suppressed amplitude and significantly, in particular here, this is significantly suppressed in the slope of that. So they want a matter power spectrum that's much steeper than what lambda CDM predicts. This discrepancy here, if you take it literally, is actually 5 sigma between the lambda CDM point and their measurements. Now, what happened this year is these authors here did some new hydrodynamical simulations in order to interpret that same data, and they found that the slope is actually more upward going than what we had expected, and the amplitude is still suppressed. So what this is telling you is that Lyman alpha isn't ready for prime time, at least this old data and these simulations, because interpreting that data and it's in two different ways with newer simulations here removes what preferred values you have for the matter power spectrum by a lot. And so it's useless for doing any constraints like this. I'm not really a Lyman alpha expert, but I know that DESI is getting many more. I mean, it's of order 100 times more Lyman alpha spectra than those previous experiments. It has better resolution, and they've been working for a long time on new hydrodynamical simulations that take into account a lot more physics. Whether they're going to be reliable enough, and they're also working with Misha and his effective theory of large-scale structure to interpret their data. I don't know. There's no paper yet from them. The data has been in the can for a long time, but
What is a hydro that's being simulated? Sorry.
so Lyman alpha is absorption of light in hydrogen clouds. And so there are these absorption lines. And what you need to simulate is the clumping of those clouds. The temperature of those clouds is important. And so, yeah, don't know what the details. So for example, these two things here are whether you're fitting for the temperature of the hydrogen cloud along with it, or whether you assume the standard value for it. All right, so that's, I think. Yeah, and then there's suppressed growth at late times. This is the thing that I'm working on right now. But let me not tell you about that because the time is really up. And I can, if you ask me after you clap about lithium, I can tell you about lithium. So my summary is, you know, there are very interesting tensions. I think the Hubble tension, I mean, to me personally, it's very puzzling. I don't actually even see how it's going to get resolved because the supernova measurements seem so robust. Other measurements are falling in line that have totally independent systematics. And then there's the CMB and lambda CDM story. Now, I don't believe in lambda CDM. I'm very happy to add new stuff to lambda CDM, but whatever you add that makes a difference for the sound horizon tends to also screw up the CMB. And it's on 11 sigma, it's very hard. So nobody has found anything that really works 100%. It could be that it's a 1 sigma, 2 sigma shift in the CMB because of experimental something, statistics, the same thing from Reese's measurement, and it's really 72 that we should be shooting for, 71. And then models, if you really push them, can get to there, but that doesn't look right. But I don't know, nothing looks right. So everybody who gives you a talk on how they exactly solve the Hubble problem, they all look like crazies because nothing really works 100%. The large scale structure tension is, from a model building perspective, is very easy. There are lots of models that can resolve the tension. I think there the data is the problem where we don't have enough data yet and good enough understanding of the data to really understand if there's a tension. So baryonic physics, for example, in simulations might, as far as we know, doesn't resolve the tension, but I don't think we're 100% confident about that. And EBN, I didn't tell you about. Thank you. Questions?
Can you quickly say what your favorite halfway solution for the Hubble tension is? Some dark radiation that changes Hubble by 5%? And what happens to it later?
Yeah, so roughly that's my favorite solution. So just adding radiation. And what happens to the radiation later is trivial. That's the nice thing about radiation. Radiation redshifts like a to the -4, and matter right around that time is starting to dominate. So it's redshifting away relative to the stuff that ends up mattering.
So because you're not trying to explain the whole thing, it's okay for it to just stay like radiation forever.
That's right. So staying like radiation is okay. So if you just add, so now you're getting into what kind of radiation did I add? So if you add free streaming radiation, that has other impacts on the CMB, in particular on the damping tail that are particularly strong and a little bit of a phase shift. And so the CMB doesn't like you to add free streaming radiation and you get knocked over the head pretty quickly. If you add self-interacting radiation, it's a little better. You get an extra 0.8 or something like that in H0. And then with NEO, we had this little bit crazy model where we have two kinds of particles in the radiation. One of them has a mass of order EV and the other one is massless. And so above an EV, you have two massless particles. Below an EV, the massive ones annihilate and go into the massless ones. So that gives you a small step in the energy density. And for some reason that we never fully understood, the CMB likes it. So the fits of the CMB improve a little bit if you have this step. And you're playing now a game of chi-squareds, right, comparing models. And so if you get something that the CMB likes and that has extra radiation in it, you get a little bit of an extra boost. That gave us another half in H0. And so we got up to 70.5 or
But
something.
roughly, like some plasma radiation that's not free streaming, that changes Hubble by 5%, your recombination is okay.
5% is more than you,
Okay, well,
more than you can do. Yeah. But yeah, I mean, you can get halfway. So the biggest thing that all of these solutions that add some extra energy density, first of all, they broaden the posterior a little bit, they broaden the error bar, that 1/2 becomes a little bit bigger, and then if you really get lucky, that also shifts, it prefers a larger value of H0. Typically, that's a fake because somebody added a one-dimensional parameter, and so you can't go lower. And so if you calculate the posterior, you move up. If you actually calculate the best fit, typically you find it's at 0. And so with the step, we found that you actually get a slightly larger 69 was the best fit, not asking that you fit Reese, just fitting to the CMB.
if you have like a standard model prime sector just mimicking us, but down by 5% or 3%, relative depth, would that do everything you want? It would have the step you want, it would have just a dark standard model, copy the standard model with the energy density 50 times smaller than us, 30 times smaller.
And no baryogenesis in that.
Yes, I know.
Yeah.
I'm thinking about unnaturalness, which would do.
Yeah, I know that, just thinking about that. I mean, and no neutrinos because of the free streaming.
Yeah.
So are we really talking about a copy? Yeah, so something like that. It is, anything that has extra radiation goes in the right direction.
And for a sigma 8, you need dark matter, dark radiation. You like dark matter, dark radiation. You need some friction, you want some extra.
Yeah.
Extra.
That's right. Yeah,
So I just wanted to ask, maybe this was part of that discussion, but I missed it. To what degree are different solutions in tension with each other? Why can't I just have 2 resolutions that add on top to get me all the way there?
good. So if you have 2 solutions for changing the sound horizon, then they are probably messing up the CM. So the typical solutions are, what am I trying to say? So it depends on what they are. If they're both changing the sound horizon through changing Hubble, then the change in Hubble is what's actually constrained. So if they're adding to, change Hubble more,
Sure.
then that doesn't work. But if you have a changing electron mass and you're changing Hubble, well, that's 2 tooth fairies, but those, that would probably help.
Okay, so they're not actually completely in conflict sometimes.
I think that's, so if they're completely different, yes, then they're not in conflict. And of course, if you're doing a little bit, if H of Z, so the energy densities today also have a little bit of a shape, maybe you can change the value of H0 that Reese extracts also a little bit. Yeah, so you can do something where you add, all your ideas together. But that's what I was saying, people who solve the Hubble tension typically look like Reese's.
If there are no more questions, let's thank Martin again.